Hello, everyone. Welcome to Principles of Programming Languages. My name is Gregory Murad Reis, and today we're going to continue on our study of formal languages. In Chomsky hierarchy, we study the regular languages, which is the simplest model of computation that solves the problem that to check if a word is part of the language or not. Pretty much what the lexical analyzer does, which is tokenizing each word that you typed in your source code. Once there are tokens and all the words you typed are part of the language, it moves to the next step. For the next step, which is the syntax analysis, we need a more powerful model of computation because regular languages cannot solve it. And this model of computation is called the context-free grammars. We have an automaton as well, which is the push-down automaton, to solve it, to express it, but we're going to talk about it later. For now, let's understand the difference and its role in the compilation. So, formal language is a way to represent the computation, especially for the lexical and the syntax analyzers. Context-free languages is a subset of formal languages, slightly more powerful than regular languages, and it's applicable in representing the structures of programming languages, and in linguistics, it's also used for natural languages. But for now, let's focus on programming languages. What are the context-free grammars? Those are rules that define the context-free languages. So we can, through context-free grammars, construct some context-free languages. So every string in a context-free language can be derived using the rules, the production rules of its corresponding context-free grammar. Okay, so in the compilation, which is the process that transforms high-level programming languages into machine-readable code, we use what is called the syntax analysis. Okay, we have multiple phases, and one of them is context-free grammar, which is checking if you can write those words in your source code in that order. And how does it do that? That's a critical phase in compilation. We've all seen your code was compiled successfully. That means that your syntax analysis was correct. So it checks if the source code that you wrote is syntactically correct. Maybe it does not make sense. It works fine, but there's still errors. It doesn't do what it's supposed to do. That's fine. But if it's syntactically correct, it passes this stage of the compilation. So if the code is syntactically correct, this phase results in a code generated. It's like a parse tree that from a single source variable, I can generate your entire source code. That hierarchical representation or composition of your code is what is called parse tree, and you can only obtain parse tree through the syntax analysis. So the structured nature of formal languages allows you to design these grammars to generate some context-free languages, and that's what we're going to do in this class. So why is it a little bit more powerful than its counterparts, DFA, NFA? We're going to do that right now. So let me share my screen now, and we're going to go over today's lecture, which is fun. I love context-free languages. So we've just reviewed this, which is the lexical analysis. So we have DFA and NFA that are used to implement these regular expressions to recognize tokens in the input source code. Okay, let's see these examples. Take some time to look at these languages. The first one looks very simple, which is the set of words where the number of zeros is equal to the number of ones. Zeros followed by ones. So what is it in this language? Let's take some notes. We have the empty, because if n is 0, I have no zeros and I have no ones, so it's the empty string. It's in the language. 0, 1 is in the language. 1, 0, 1, 1. 0, 0, 1, 1. 0, 0, 0, 1, 1, 1. As long as the same number of zeros and ones in the string, this string is in the language. What is not in the language? 0, 0, 1, it's not, because the number of zeros is different than the number of ones. So can I design a DFA or NFA to represent this? And how? Let's think about the design. So In a DFA, if I read the first 0, I cannot accept. I have to read another 1. Okay, and then I can accept. But how do I allow for 2 zeros, 3 zeros, 4 zeros? If I do a self loop on 0 or 1, I allow as many zeros or 1s. I lose track of how many zeros we read. So self loop is too powerful. We lose track of the number of occurrences. So how is the only way we have to count? So we have to have a DFA for 1, 0, and 1, 1. We have to have a DFA for 0, 0, 1, 1. We have to have a DFA for 3 zeros and 3 1s. We have to have another DFA for 4 zeros, 4 1s. So we have to have infinite amount of DFA to solve this problem, because there's no way I can count. That's the verb that is important here. I cannot count the number of occurrences. And for a word to be in the language, I need to be sure that the number of zeros is equal to the number of ones. If I can't count with DFA or NFA, it's not powerful enough to represent, to express this language. Similar reasoning occurs with B. Has an equal number of zeros and ones in any order. I need to have a DFA for each amount of zeros in my language. This is very weak. So DFA and NFA are very, very weak to solve a problem like this one, because we can't count with DFA and NFA. Similarly, in C, has an equal number of 0, 1, or 1, 0. One DFA for each number of 1 zeros, 1s, and 1 zeros. In D, it's even harder problem. The word has to be equal to, the word has to be followed by itself. So Greg, Greg, FIU, FIU. In E, I need to count the occurrences of 1 based on a criteria n squared. I also need to count. And in F, zeros followed by 1s, as long as the number of zeros is always greater than a number of 1s. The only way I can accomplish that is having infinite amount of DFA or NFA to account for the number of zeros and the number of 1s. So you see that the common pattern I extract from these problems is that I can't count. So DFA and NFA regular languages, not powerful to solve this. I need something more powerful. We go up in Chomsky hierarchy to another class of formal languages, which is the context-free languages, that introduces something called recursion. So recursively calling a variable on itself, I can make sure that every time I add a character 0, I add another character 0 in its opposite position. So every time there's a 0, there's another 0. I can also create a variable that can be replaced by 0 and 1. So every time I add a 0, I add a 1. So this way I can keep track of how many zeros and ones I add at each moment in the derivation. I can only accomplish that with what we're about to study, which is context-free languages. We can't do it with DFA and NFA because we can't count. So Greg, so how do I design that graph, the DFA, the automaton? In the case of context-free languages, I design the automata and I have to have an extra space, an extra part of the memory, which is a stack. By introducing the stack, I can add this recursion feature to my computation and I'm able to count because I have a separate stack. So I cannot simply draw a DFA, NFA, just the way we've been using it to represent context-free, because we need an extra stack. It's a very interesting process. For now, let's work on understanding better the context-free languages and designing some of the grammars, writing some of the grammars to generate a certain language. I always show my students the Chomsky hierarchy, regular through DFA, NFA, simplest model of computation. 1 up, context-free languages generated by context-free grammars represented through push-down automata. Push-down automata, think of it as DFA, NFA plus a stack. Slightly more powerful model of computation. So almost all the syntax analysis based on the rules of a grammar that is context-free for programming languages. So that's why it's important for us in this course to study context-free grammars. So the most important component of context-free grammars is the rules, the set of rules that we have to generate the languages. We have variables, we have the terminals, similar to the characters we had in DFA and NFA, and it's similar to this. Oh, before we get there. So when a compiler translates your code into another form that the machine will understand, it involves the parsing, the semantic analysis, optimization, finally the code generation. We are in the parsing. part of that compilation, okay? So it's analyzing your input code, lexical analysis, check if each word is in the language. Next, which we're doing right now, we're checking if you put all those words in the correct order, following the rules of the grammar. If we can regenerate your code from one single source variable into your entire code that you wrote using the rules, we build this hierarchical structure that is called parse tree, okay? Semantics, which is the next step, is gonna check for errors that, even though it passed the syntactic analysis, maybe later on in the execution, there might be some other issues like type checking. Maybe there will be some problems with type as your code executes, some name resolution that you might have done wrong, scoping rules, and some other semantic rules specific to the language that you chose. So maybe it will go through the syntax analysis, it's syntactically correct, but it might fail in semantics. So this is the next step. Optimization is the study of various techniques that improves the efficiency and the performance of the generated code. Simplification, constant folding, loop unrolling, and any other type of features that you can implement. And code generation is translating this optimized parse tree, if it was able to be optimized, into assembly or machine code, so that can be executed by the system you're using, okay? So let's go back to the context-free. As I mentioned, context-free grammar is slightly more powerful than regular because of this recursive feature that allows us to not count, but at least keep track of how many occurrences of zeros and ones or other characters. It was first used in human languages in the study of linguistics, relationship between noun, verb, prepositions. In the textbook, you can see more about that. For us, in our course, it's important because it's part of the specification and compilation. It's part of the syntax analysis. And every time there is a design of a compiler or interpreter, the first thing they need to do is think about the grammar, the set of rules to generate that language. Okay, so most compilers and interpreters contain a component called parser that will extract the meaning of a program, which is the syntactic part, the parse tree, before generating the code that the machine will understand. Finally, the formal definition. It's a four-tuple, some set of variables, some set of characters, some set of rules, and the start variable, the one that from that variable I will try to generate your source code. That's it. So the collection of languages associated with context-free grammars that can be generated by context-free grammars is called context-free languages. This is a simple example. So here we have a variable. Usually we represent the variable with capital letters, and we represent the characters with lowercase letters. So in this case, S and B are both variables that can be that I can substitute with another variable or a character. So the start variable is S because it's right in the left and top row. Okay, so that's my start variable. So if I have a variable S, what can I replace S with? I can replace that variable with either character A followed by variable S. You see the recursion there? From S, I'm generating A and S concatenated. So that S can be replaced further. I can replace a variable until there are only characters. But S can also be replaced with a variable B. So that horizontal, that vertical line that you see there in the same row means or. It's either AS or B. So you can replace S with either one of these productions. And B in turn can be only replaced by a character terminal B. Let's see some more interesting examples. So let's say, for example, I want to derive a string AAAB. So we know that S can be replaced by AS. So I generate the first AS. Oh, still have a variable S. I can replace that variable with another AS, another production. Oh, there's still S. I can replace that S with AS. So I have AAA variable S. Now I can replace S with a B because I want to reach the terminal B. And B can be replaced by the terminal B. I was able to generate finally the string AAAB. You can also represent it through a parse tree, which is the hierarchical format. From S, I generate AB. S, I generate, I'm sorry, AS. S, I generate AS. S, I generate AS. S, I generate AB. Finally, B generates B. You know that all my leaf nodes are characters. When I reach the case where all my leaf nodes are characters, terminal in my language, this was generated by that grammar, AAAB. Okay? So all the strings generated by a context-free grammars is part of the context-free language. So we say that the language of grammar 1 is the language generated by that grammar. That previous case, the language that it generates is A to N followed by 1 only B for any N greater or equal to 0. Okay? So let's see some more examples. There are some parsers. There's also a classification of parsers where you have top-down parsers. So from a single source variable, you generate all the characters, which are the leaf nodes, or you can do bottom-up. Starting from your code, you try to come to a single variable. So we know we have top-down parsers and bottom-up parsers, okay? One of example of top-down parsers is the recursive descent parser, and it's usually used for the compilation process, okay? So once the parse tree is constructed, it can be used for further processing, maybe semantics, optimization, finally code generation for the machine. So context-free grammar is a formalism that specifies the syntax, the set of rules for a certain programming language so that it can be transformed into machine code. So parsers are programs that uses the rules of the context-free grammar to generate that parse tree and saying syntax analysis correct, your code is syntactically correct. So use the grammar to describe the language, generating each string of the language. Okay, so let's say this first example. This grammar number 2 has one variable S, two terminals A, B, and it has 3 rules. And the start variable, obviously, is S because there's only one variable. So S can be replaced by ASB or SS or empty string. So how do I generate, for example, AB, AB? So from S, I can generate variable S followed by variable S. Now let's do leftmost derivation. If we do that, we always replace the leftmost variable until finally we reach a case where we only have final terminals characters, okay? So from S, I generate SS. The first S can generate ASB. So that first S generated ASB. Now I still have a first S here, which is between these two. I can generate empty. So ASB turns into AB. Now there's that last S there. So what I have here is that S can generate another ASB. That S can generate empty. Finally, I generate AB, AB. Okay? So this is generation. Here I put some other examples for other strings. Okay? This is how we generate the following strings. We may also represent it through a parse tree. Let's say we have this example. This grammar generates the algebraic expressions of multiplication and addition using the parentheses. This is the grammar for it. So if I want to generate A plus A times A, we know that starting with the start variable E, I can generate E plus T, then following each one of these variables, I can reach the terminals A plus A times A. In the next video, you'll see more examples of me doing this on the iPad and more exercises to come for you to practice, okay? You can also generate parentheses A plus A times A. So how to design? It needs creativity. It's trickier than finite automata because you have to think about the rules, and now you have to think recursively because you have a variable generating another variable. Don't worry, we're going to do more examples very soon. Sometimes context-free languages are the union of other context-free languages, so it's good to practice problem decomposition. Break down your problem into subproblems so you finally merge them two into one variable, and you can solve and construct the entire grammar. So for example, 0 to n, 1 to n for any n greater or equal to 0, union with 1 to n, 0 to n for any n greater or equal to 0. It's easy. Do one at a time. Remember, we were not able to solve this earlier on in this class using DFA and FA because we needed one DFA for each end. There's no way for us to count the occurrences of zeros or ones. But with a simple recursive rule like this one here, S generates 0S1. Every time I replace S with this production, I'm adding a 0, a variable, and a 1. And that variable in the middle can be replaced by another what? 0S1. So every time I add a 0, I'm also adding a 1. That way I keep track of how many zeros and ones I have, because for every 0, there's a 1. And I solve that with a simple rule that allowed for recursion in the middle. I was able to solve a problem that would require an infinite amount of DFA. Now you see why context-free grammars are more powerful. Or if I'm done, if I have the number of zeros and ones that I want, I can simply produce an epsilon, right? The empty string between that 0 and 1. Similarly, if you want to generate 1 and 0, you can create another rule that takes you to 1, variable, 0, or empty. Since it's one or the other, union is or, you can create a single start variable that can generate either one path or the other. This is similar to what we did in the NFA in a previous lecture where we had 2 epsilon. This is similar, right? We have one variable that can either derive S1 or S2, okay? So following these rules, you can generate all the words that are in this language. 3 variables, 2 terminals or characters, set of rules, and my start variable. So let's take a look at some exercises that we need to design the context-free grammars, which means write the rules to generate the strings, all the strings in the language. So first I start with the language. That's the first thing, because we need to create the rules that would generate all words that are part of this language, okay? The first language here is the set of words such that each word contains at least 3 Bs. So you need to create a rule that has 3 Bs, and then we need to think about what can occur before the first B, between the first and second B, between the second and third Bs, and after the third B. So let's think about it. The sigma, the alphabet, is A and B. So we can have A's or B's before the first B, A's or B's in any order between the B's, and A's or B's in any order after the B. So there's no restriction on A's and B's as long as I have 3 B's. So what we can do is we create one rule. That accommodates these 3 B's. So I can create a rule starting in S, which is the variable, that generates BBB. Between the first B, I create a variable that generates any amount of A's, any amount of B's. So I recursively call X on AX and BX. Or nothing, or empty. Maybe there are only 3 B's, nothing else. So I need this X to also produce empty. The same thing occurs between the first and second B's. Anything. What is anything? It's a variable X that can generate any amount of A's or B's in any order. That's why X can produce AX or BX. X in turn can generate more A's or B's or empty. The second example here is the word is equal to its reverse. So when I write WR, it means that it's the reverse of that word. So in this case, it's a palindrome. The word is equal to its reverse. And the length of the word is even. So if the length of the word is even, okay, so an empty string is okay because the length of empty string is 0, that's even, and the reverse of an empty string is an empty string. So the empty string should be accommodated. So how do we go about this problem? So let's think for a second, how do you make a word equal to its reverse? So the first element needs to be equal to the last element. The second element needs to be equal to the second from last, so forth and so on. So what I need to do is create my upper bounds, then the second and the second to last, third and third to last, until it converges, until I have the middle here, the middle point of my string. So I need to generate first, the outermost ones, and they have to be equal. So if the first one is 0, the last one has to be 0. If the first one is 1, the last one has to be 1. Now the second and the second to last. If it's 0 here, it's 0 here. If it's 1 here, it's 1 here. So forth and so on. So I can create a variable in the middle of two what? 0, 0 or 1, 1. That way I generate my palindrome. Oh, I'm sorry, in this case it's A and B's. So it's the same procedure. So I have some rules that S can generate A as A or B as B. That way, I guarantee that in the position where I put an A, there's also a mirrored A in the end. And if I put a B in a certain position, there's also a B mirrored in the end, or empty. Why empty? Because the middle symbol, right in the middle of the string, has to be empty to guarantee that the length is even. If I add one symbol in the middle, that automatically makes the string even. Why? Because you're always adding two characters at a time. If you put one single symbol in the middle, it will turn that length into an odd length. And we don't want that. So the middle symbol in the end has to be empty to guarantee that it's even. And it's palindrome. The next example with A and B's as well. The length is odd and the middle symbol is A. So to guarantee that it's odd, I need to add two characters at a time. It doesn't have to be the same in the mirrored position. So it's not a palindrome. So if I add an A in the first position, it can be A or B in the last position. So I already have two rules here, AB or AA for the outermost ones. But if I start with a B, I can have A or B in the last position. So I have two more rules. So I already have four rules here because it can be any combinations of A and B's. So I always, for every derivation, I add two characters. That makes the length even. To make the length odd, I add one element in the middle, and that middle symbol has to be A. So I cannot produce empty. I have to produce A. So the answer is S can derive A as A, B as B, A as B, because can be A and B, doesn't matter, as long as you add two elements at a time, or B as A. And in the end, this middle symbol will be A, because I'm going to replace that middle variable to an A, and I have only characters. Now I have 0 to N, 1 to M, 2 to 2N. Let's understand this. N and M can be any value starting 0 or higher. So 0 and 2 are related. 2 is dependent on 0, which means the number of 2's is dependent on the number of 0's. First, it's 0's followed by 1's followed by 2's. But the number of 2's is double the amount of 0's. 1 is independent. The number of 1's is independent. So I can break down my problem into two cases. I have to take care of the 0's and 2's, 0's and 2's. And in the middle, I can have any amount of 1's. It doesn't matter the amount of 1's. So in my answer, I have to think. First, I have to create a rule that adding a 0, I add two 2's, because 2's is always double. So let's say I replace that A with another production A, 0A22. It's going to be 0, 0, A, 2, 2, 2, 2. So every time I add a 0, I also add two 2's, guaranteeing that the number of 2's is double the number of 0's. How about the 1's? I can generate from A a variable called B that can generate any amount of 1's, including empty. Okay? A can go directly to B, and then B goes to empty, because the empty string is also allowed. Okay, the empty string is also allowed. Notice that N can be equals to 0. So I have no occurrences of 0 and I have no occurrences of 2. That is totally fine. So the path to reach the empty string is A produces B, B produces empty. Okay, but if there's at least one 0, there are two 2's. If there are two 0's, four 2's, so forth and so on. In my next example, I have 0 to I, 1 to J, 2 to K, where I has to be equal to J. Now, 0 is related to the number of 1. So I have 0's followed by 1's. They have to be the same length, each 0's and 1's substring. And 2 is independent, any amount of 2. So I can decompose this problem into two. First, let's think about the overall scenario. So 0's and 1's is one substring. So I have to create a variable for this substring. And 2 to K is another substring that will work independently. So let's create a variable for each one of them. So I can create one variable B concatenated with C, and B will take care of the 0's and 1's, C will take care of the 2's. So let's think about B first. B, every time there's a 0, has to add another 1. So I can create a recursion in the middle for 0's and 1's. 0, 1, 0, 0, 1, 1, 0, 0, 0, 1, 1, 1, so forth and so on. Good. How about C? That concatenated variable C can take care of any amount of 2's you want. So I can have C go into 2C. So you can produce a billion 2's or no 2's at all, because C can also produce empty. I, J, and K, the three of them, greater or equal to 0. In the case that I, J, and K are equal to 0, you need the epsilon transition as well, the epsilon production, so that A can also produce epsilon directly, B can produce epsilon, and C can also produce epsilon. In this example, I, J, and K can only be greater than 0, so I cannot allow for empty. So there is at least 1, 0, and 1, because they are dependent on each other, and at least 1, 2. So it's similar, but let's think for a second. I have to have a 0 and 1. So in my rule here, when I create A to B and C, I cannot produce epsilon at all. But my B has to be at least what? 0, 1. That's the minimum requirement, to have at least 1, 0, and 1, 1. But if I want more, 0, B, 1. I do that recursion in the middle. And my C, any amount of 2's, but at least 1, 2. So if I need 1, 2 only, I produce C directly to 2. If I need more than 1, 2, first you call 2C, and then you replace that C with another 2. Produce 2 2's. That's example 10. In example 11, that's very interesting. It's also 0 to I, 1 to J, 2 to K. I, J, and K, the three of them can be greater or equal to 0. But here I have two problems, two subproblems. I is equal to J or I is equal to K. So let's decompose. First, I is equal to J. We already did that, right? I create two variables, B and C. B takes care of 0, B, 1, the same amount of 0's and 1's. And C can be any amount of 2's. We already did that subproblem. We have the answer for that subproblem previously. Now let's think about I to K. So if 0 is equal, the number of 0's is equal to the number of 2's, I need to create a variable that takes care of that produces 0, variable, 2. So every time I add a 0, I also add a 2. And what can I have in the middle? Any amount of 1. So I can also have a rule that produces any amount of 1's in the middle of that 0 and 2. Any amount of 1's. So my answer will be A goes to B and C, which is that first subproblem, and B is 0, B, 1, or empty. C is to C or empty. I solved that I equals to J problem. B and C are separated. Now I created a second rule to take care of the second subproblem where I is equal to K. In this case, D is 0, D, 2. So every time I add a 0, I add a 2. I guarantee that the number of 0 is equal to the number of 2's, because there's no way to produce a 0 without a 2 and vice versa. But that D can also be any amount of 1's. So I go to a second variable, E, and that E produces any amount of 1's, including empty. W begins with a 0, ends with a 1, and contains 1 or more 2's. Okay? So it has to begin with a 0, it has to end with a 1, and it can contain 1 or more 2's. So first, let's take care of that restriction. Starts in a 0 and ends with a 1. So every time I start a derivation, I have to start with 0, A1. Easy. Now, what can A be? A can be a bunch of 0's or a bunch of 1's, or how do I reach the epsilon? I need to reach the epsilon to form my final string. But the only path to producing an epsilon is having at least what? 1, 2. So that's why I put 2b. I create a new rule so that I have to use that rule to reach the epsilon. Otherwise, I'll never reach the epsilon. But why do I need that rule? To guarantee that there is at least 1, 2, which is part of the language, right? In the description of the language, it says it contains 1 or more 2's. So if I take that path with 2b, I can add more 0's, I can add more 1's, I can add more 2's if I want, or epsilon, because I already read the 2 that is required. I hope you enjoyed these examples. There are more exercises for you to work on. So let's do a quick review here. So syntax analysis is the part of the compilation that analyzes the syntax, right? If it's syntactically correct, if you wrote all the words in the correct order following the grammar. It does that by producing a parse tree, which is this hierarchical structure where from a single source variable, I can generate your entire source code following the rules, so it's synthetically correct. So context-free grammars generates all the context-free languages, and it's used to specify the rules for a certain programming language. And parsers are the programs that are used to build the parse tree to guarantee that your code is synthetically correct. Lexical analyzer, we learned, check if a word is part of the language or not. It's like a pattern matching. It can be done through finite automata, either DFA or NFA. More high level here, syntax analyzer or parser checks if you put all the words in the correct order following the grammar, the rules of the grammar. You can do that mathematically through push-down automata, which is similar to DFA NFA, plus the stack, that extra space of stack, so you guarantee that recursive feature. Which recursive feature? Remember when we had A generates 0, A1? That recursion. And this syntax analyzer can be either top-down from a single source variable. You generate your parse tree from that one. So the leaf nodes are all your strings in your code. Or it can be bottom-up. From your source code, I try to generate a single source, okay? Through those fragments. Thank you very much, and I hope you enjoy. Don't forget to do all your exercises to design more context-free grammars.